Hi, we're the Ocean Going Robots ECE Capstone team. Our team is Malachi Fisher, Grayson Lewis, Miles Drake, and Samuel Barton. Our project for this year is to develop a system to measure swell amplitude, direction, and period of waves from the Slocum glider as it floats on the surface of the ocean while consuming a minimal amount of power.
Our goals from last week were to look further into the SD card that we'll be using for data transfer, becoming more familiar with the STM32 programming environment, investigating interfaces between the STM32 microcontroller and the micro SD card, as well as investigating micro SD card power consumption during the read and write sequences.
To further familiarize ourselves with the STM32 development environment, we followed code examples to communicate to a computer via a COM port. We wrote a short program to print hello to the serial port each time a button was pressed. We also started reading the documentation and STM32 example code to interface with the XSense IMU, which is the shield on top of the white Nucleo board. So we also procured the XSense IMU development kit and were able to perform initial testing of it. We installed the software provided by XSense, and we were able to connect the XSense and view a visualization of the IMU data. And we're currently working on interfacing that with the STM32 and communicating directly.
Another thing we did this week was put together the top level block diagram for the system. We created blocks to represent each of the different components of our system, and we drafted the interface definitions between each of these blocks. We split some blocks into more blocks to satisfy the project requirements of having 2 blocks per person at least. For instance, we split the firmware block into the different sections of firmware for controlling the XSense and the SD card and serial to the science computer. We're currently working on translating this block diagram into the Capstone portal software.
So what we learned about the SD cards last week was that they're expensive to write to, but they're less expensive to read from. The peak write current that is typically seen is upwards of 100 milliamps, but the average use current, which takes into account read, write, and standby time, is around 25 milliamps. The standby current itself is typically in the microamp range. We also realized we will have to do multiple writes to the SD card during the glider surfacing. There's not quite enough RAM storage on the STM32 to hold all the data it's going to collect. So we'll need to write at least twice per surface in order to make sure that everything gets stored onto the SD card. We also believe we'll be using an SPI protocol to communicate between the microcontroller and SD card. This isn't set in stone though, and it may change after we look into the power consumptions of the different protocols, as well as some other SD card specs. We realize we'll only be needing less than 1 gigabyte of memory to store all the data for a 3-month deployment, which allows for a lot of freedom in SD card memory sizes. We did learn that less memory implies higher efficiency typically, which would be great for us since we have a very tight power budget.
This week for the project document, we finished the initial draft of section 3 of our project document, including our block diagrams, our block descriptions, and our interface definitions. And we've continued to implement the instructor feedback from sections 1 and 2 of our project document. Our goals for this week, next week, are to finish project document section 3, which is finalizing our block assignments. We're also going to finish implementing the feedback for project document sections 1 and 2, including notifying our project partners of any changes in those documents. We're going to complete the block diagram and interface definition draft and hopefully successfully interface with the XSense using the STM32 card. In addition, we're going to have a happy Thanksgiving.